So hello everybody. Today I'm going to talk about the axially symmetric figures of the plane. First, as you can see, is a definition, what we mean by a figure being axially symmetric. And the definition says that if there is a line, let's call it T, such that the figure is invariant when reflected about line T, then we say that this figure is axially symmetric. Remember last class we talked about what it means that something is invariant when reflected or when any kind of geometric transformation takes place. It means that although points move when you find their image point, the figure itself does not change. So let's see this isosceles triangle, which is, as we know from our previous studies, is axially symmetric. So there is a line T, this is a line T, such that the triangle is invariant when reflected, where actually point C is a fixed point, but all the other points of the triangle are such that their image is on the other side of the axis. So this is going to be actually the image of A dash, and the image of B is going to be the original A vertex. But any other point I would choose on the triangle, let's say I choose this point, then the image will go on the other side of T, but it will still be on the triangle, since an isosceles triangle, a distance from the axis of P point is the same as the distance of P dash from the axis. So the figure is invariant when you reflect it, as if folding it along the axis, it doesn't change. Another example is, for example, the circle. Every circle is axially symmetric. You just have to draw one of the infinitely many diameters which go across the center of the circle, and any of the diameters serves you as a T, the axis of symmetry. And then if you pick any point of the circle, then obviously this point from the center is the same as its image is going to be. Therefore, it's going to be also on the circle, the image. And any point you pick, its axially symmetric pair is going to be again on the circle. This actually forms, as you can see, the two radii, and this dashed line forms an isosceles triangle. So this is the not special case when a triangle can be axially symmetric is the isosceles triangle. And in this case, you have one single axis, and this axis is actually the perpendicular bisector of the base of the triangle. So we just remind you of this vocabulary, which you already know. And it follows from the property of axial symmetry or line deflection that we revised last class, that alpha and beta are the same. So actually, I can write here beta, but I can also write here alpha because they are the same. So the two base angles of the triangle are the same because of the axial symmetry. When I reflect this angle, it goes back to the other angle of the base. It's also a property of axial symmetry that this angle, when this line is reflected to the axis, it goes into the other line, which ends up to be the leg of the triangle. So they are equal angles. So actually, the axis bisects the vertex angle. The vertex angle is the angle which is opposite the base in an isosceles triangle. If, however, your triangle is more special than an isosceles triangle, then we talk about equilateral triangles. And we know that equilateral triangles have three equal sides. So basically, no matter which side you pick, it all behaves as if it were a base of an isosceles triangle. and therefore it follows that you can find 3 axes of symmetry which actually correspond to all the special lines of the triangle. The angle bisector of this angle is the perpendicular bisector of this segment, and it's also the altitude of the triangle. So this is a very special case. Equilateral triangles are the only triangles which have 3 axes of symmetry. Okay, let's turn our attention to axially symmetric quadrilaterals, that is, figures which have 4 vertices. According to where the vertices are situated with respect to the axis, we distinguish 2 types, type 1 and type 2. Type 1 is when none of the vertices of the quadrilateral lie on the axis, so no vertex is on the axis. If this is the case, then because the figure is axially symmetric and the vertices are not on the axis, if you pick any vertex, its mirror image has to be the other vertex, and similarly, the other vertex also has to have a mirror image because of the axial symmetric property. So it follows that you are going to end up with a figure which has 2 bases, let's call this way, 1 base, 2 base, whose perpendicular bisector has to be the axis. So this axis is the perpendicular bisector of base AB and also base CD. It also follows from the axial symmetry that segment AD, which is the side of this figure, is equal to segment BC since they are each other's mirror image. This figure, the simplest figure with this property, is the symmetric trapezium. And as I just told you, 3 properties immediately follow from the symmetry. The first property is that the 2 legs, so AD, is equal to BC. These are the 2 legs of the trapezium. This was one property. The second property is that axis T is the perpendicular bisector of the 2 bases AB and also BC. These are the 2 bases. And there's a third interesting property which also follows from the symmetry of the figure. Namely, if I draw one of the diagonals, let's say I draw diagonals AC, and I think about its mirror image reflected to T, then this is going to be the fixed point because it's on T. The image of C is D, so this is going to be on the image of the diagonal. And this point of the diagonal is reflected to B because of the symmetry. So actually what I get is that the mirror image of the diagonal AC is exactly the diagonal BD. So it follows that the 2 diagonals must be of equal length. So 2 diagonals are equal. Of course, we are talking about lengths. Okay, so that's type 1. Of course, there are special cases, like, for example, the rectangle is a special symmetric trapezium. Why is it special? Because apart from the properties of a trapezium, namely having 2 parallel sides, it also has the property that it has 4 right angles, and it follows from that it has actually 2 axes of symmetry. Okay, let's see type 2. Type 2 quadrilaterals with axial symmetry are the ones which have one vertex. There is a vertex on the axis. Now let's pick this D, and it is on the vertex. It follows if there is one vertex on the axis of symmetry, there are 2 points on the axis of symmetry. The other 2 vertices are each other's mirror images. So the mirror image of A is A dash, which is C, and the mirror image of C is C dash, which corresponds to A. Furthermore, it follows again that this segment till the axis is of the same length as this segment. So the axis is, T is, the perpendicular bisector of the other diagonal is the perpendicular bisector of the other diagonal, which in our case is AC. But notice that this is only true for that special diagonal, which is the axis itself. The other diagonal doesn't bisect BD, since this is much shorter than that one. The second property which follows from the axial symmetry is that the diagonal which corresponds to the axis bisects the angle. This angle goes into that, so it's an angle bisector of the angle at vertex D. Similarly, this angle is going to be the mirror image of that angle when you reflect. So again, the T line is an angle bisector of the whole angle at vertex B. So that means that the axis, so the axis T, is an angle bisector. In this particular case, let's call this beta and delta of beta and delta. Okay, so that's another property. And the final property, which follows from the axial symmetry, is that segment AD is going to be the mirror image of segment DC, so they have to be of the same length. Similarly, segment AB is the mirror image of segment BC, so they are also of equal length. So that means that two pairs of adjacent sides are of equal length. Sides are equal. Okay? And once again, it doesn't mean that the kite is the only type of axially symmetric quadrilateral. For example, the square and the rhombus, I'm trying to make it a rhombus and not a parallelogram, are subcases, because if you take this vertex, this axis, then everything is going to be like in a kite with a special property of having full right angles and all sides equal. And if you take the rhombus again, you have two axes of symmetry going through the vertices. This is the right angle here, and all sides are equal. Typical mistake, which you have to be careful about, if you take a parallelogram, which is not a rhombus, so basically I'm trying to make it very parallelogram-like, so basically the two sides are obviously not of equal length, so let's say AB, AB. You don't have an axis of symmetry. Usually, two candidates come into the picture when we think about it. Oh, maybe this is an axis of symmetry. Well, that goes really wrong, because if I draw this, you can see that the mirror image of this point is going to be somewhere here, so it's not going to be an invariant figure. So, okay, then let's try the diagonal, which goes through two vertices, like in the case of rhombus, kite, and square. But again, I have a problem, because if you look at it, this is the axis of symmetry, so vertex A is going to have its mirror image, let's construct it, somewhere here, which is obviously not on the parallelogram. So this is not an axis of symmetry of the parallelogram, because the parallelogram doesn't go into itself when reflected. The figure is not invariant. Okay, so this concludes axially symmetric quadrilaterals and triangles.